So I was asked to speak about some of the work that we've been doing with crustal xenoliths in the Rocky Mountain region. And so I'll summarize some of the results that we've obtained from geochronology, from petrology, from physical property characterization, and how we've been trying to integrate that with seismic observations to say something about the history and the origin of modern structure in the deep crust in the Rockies. I'll give you a little bit of, or I'll give you some information about two examples. The first and most of the talk will cover some studies that we've done in central Montana. And this is going to be primarily in the context of the nature of a high velocity lower crustal layer that underlies much of that region. And then the second example will be just a brief intro to some work that we're doing now with looking at the timing and the nature of late stage hydration in crustal xenoliths from the Colorado Plateau. So I'll just start with this compilation from Christensen and Mooney that just shows average P-wave velocities for versus depth for different types of tectonic settings. And this is just to point out that high velocity lower crustal layers, when defined as greater than 7 kilometers per second, or sometimes referred to as 7x layers in some of the literature, are not that uncommon, certainly in some types of settings. But what's interesting about the region around Montana and Wyoming is that locally there's an anomalously thick layer of high velocity material that appears to contribute to as much as half of the crustal column. A number of different mechanisms are known to be capable of producing this type of high velocity material. Magmatic underplating is probably one of the more prominent mechanisms associated with flood basalts, for example, or rift settings. Mechanical underplating mechanisms have been proposed. Somehow oceanic slivers of oceanic crust might become underthrust. This is an example from the South Island of New Zealand. But also magmatic residue associated with arc construction is another common mechanism. So there are a number of different ways that this type of material can be produced. This is a compilation of pre-EarthScope refraction lines across the U.S. that just is useful to show where 7x layers or high velocity lower crustal layers have been observed in the past, and those are shown in red. Where they apparently are absent are shown in yellow. And then some xenolith localities are also shown here with the black stars. I'm going to zoom in very quickly to the region in the northern Rockies around Montana and Wyoming. On the left is a map that shows a roughly north-south line. This is the trace of the deep probe SEREX seismic refraction experiment that was ran in I think the mid-90s. And the profile is shown on the right corresponds to that line, and it shows the P-wave velocity structure with the 7x layer shown in yellow that underlies the Medicine Hat block. It's labeled MHB. That is an Archean block along the Canadian border, the Great Falls Tectonic Zone, GFTZ, and the Wyoming Craton. The Great Falls Tectonic Zone is commonly considered a collisional suture between those two Archean blocks. This map is similar scale, zoomed in a little bit more, but shows a little bit more geologic context. The north-south line, again, is the deep probe profile. Some other seismic stations are shown here, U.S. array stations. The Bighorn EarthScope project, the seismic footprint of it is shown in red. Laramide basement chord uplifts are shown in brown. The Belt Basin supergroup is shown in pink. The Great Falls Tectonic Zone is shown as these gray dashed lines. This is the general extent of the Great Falls Tectonic Zone. It's largely buried. Again, it's been interpreted as a collisional suture that developed between about 1.8 and 1.7 billion years ago. It's largely buried, but there is evidence for subduction-related magmatism that it crops out in the Little Belt Mountains, and then there's quite a bit of high-grade tectonism in the exposed rocks in southwestern Montana that are probably related to this orogenic event as well. The xenolith localities are shown with the white stars, and these are xenoliths hosted by Eocene, circa 50 million year volcanic rocks. So just skipping details of the petrology and the geochronology, I'm just going to show or summarize some of the results. A number of these xenoliths from central Montana record evidence for an early metamorphic event that occurred around 2.1 GA. At least one of those suggests that in that xenolith, the metamorphism occurred at relatively low pressure. We infer that this metamorphism was related to advective heat, probably from intraplating magma associated with an early rifting event that is suspected to have occurred along the margins of the Wyoming Craton. A number of xenoliths record significant increases in pressure. At least one of those has been dated at about 1.79 GA, so that's the timing of the Great Falls tectonic zone. So we infer crustal thickening to explain those increases in pressure. A number of xenoliths also show evidence for tectonic decompression, and at least one of those has also been dated at about 1.7 GA, so part of the same tectonic cycle. And the point of this slide is to show that the crustal xenolith suite in central Montana as a whole records a fairly dynamic and complex history that is unlike what you might expect for a simple magmatic underplate, where you might expect more of a constant sort of isobaric heating or isobaric cooling metamorphic history. So putting that information and some other information that I've skipped over together into a different form, this is just a schematic time series that illustrates some of the main tectonic events that we think these xenoliths probably experienced, and each one of these episodes, I'm not going to walk through this in any detail, but each one of these episodes is recorded both directly in the xenolith population, but also in the surface geology around the Wyoming Craton as well. And probably during each one of these episodes, there was some magmatic addition to the deep crust. The thickness that we see today of the high-velocity lower crustal layer is probably not just due to magmatic thickening, but rather there were extensional events, there was a collisional event throughout the history during this time frame. And so each one of those events probably contributed to the overall crustal thickness of the crustal column. So to the physical properties, I'm primarily going to be showing data about calculated bulk seismic velocities. So these are P-wave velocities calculated from Hacker and Aber's physical properties database. And shown now with the gray band is the 7X layer, top and bottom, as defined by the deep probe seismic refraction experiment. This is from a study by Gorman et al. And the first thing to point out is that of the deeper xenoliths that are probably derived from within this high velocity layer, there's quite a variation in the calculated velocities, anywhere from about 7 kilometers per second up to about 8 kilometers per second. So the blue lines that I've just shown on there now are MOHO picks from U.S. array stations that are closest to the xenolith localities. The Sweetgrass Hills locality, SGH, is the locality close to the Canadian border. The MOHO pick there is at about 39 kilometers. The stations that are closest to Homestead and Robinson Ranch are at about 42 kilometers. These are from the study by Hirsch Gilbert earlier last year from the U.S. array data conventional receiver functions. So this is in contrast to the depth of the MOHO as picked from the seismic refraction experiment from the deep probe line, which is at 58 kilometers in central Montana. And as a seismologist, this discrepancy kind of freaked me out, and I'm still a little freaked out by it, I suppose. But if it weren't for that magnitude of discrepancy between where is the MOHO, I don't think I'd have the nerve to suggest that the crustal xenolith data might be a little bit clustered. And so I'm going to suggest that perhaps there's a shallower cluster with velocities that are closer to 7 kilometers per second, and then a deeper cluster that is closer to 7.5 or greater kilometers per second. And perhaps the receiver functions are seeing an interface that is actually within the high velocity deep crustal layer. As I understand it, receiver functions are more sensitive to impedance contrast rather than absolute magnitudes of velocities. And so perhaps there's an interface within this high velocity layer that those are seeing. I think that concept might be a little bit more likely if the interface, the velocity contrast across the crust mantle boundary at a greater depth is somewhat diminished. And so these are calculated velocities from 17 spinel facies upper mantle xenoliths from the Bear Paw Mountains whose compositions were reported by Downs et al. In 2004. This is from a locality that is the Bear Paw Mountains is the same locality where Robinson Ranch and Little Sand Creek crustal xenoliths are from. So those are the triangles and the circles. And so the thing about these mantle xenoliths is that they're heavily metasomatized. The majority of them are metasomatized to the point where they contain 10% or more phlogopite, so biotite. And that 10% cutoff is shown by this little black bar. So everything to the left of that bar represents upper mantle xenoliths that have 10% or more phlogopite in them. And the point is that these calculated velocities, the range is huge, to the point where almost any combination of these uppermost mantle samples versus the lowermost crustal xenoliths might provide a much diminished velocity interface across that crust mantle boundary. So this is a study from Yu et al. From the North China Craton that shows a comparison of two different seismic techniques. The panels on the left and the right are identical. The ones across the top are from a technique that they call virtual deep seismic sounding, which, as I understand it, uses a teleseismic wave as a reflection source. And the MOHO picks from this technique are shown by the dashed red lines. And then the bottom panels are stacked conventional receiver functions. And so the MOHO picks that apparently have been chosen from several previous studies are with the prominent arrival at about 5 seconds, and those are shown by the green dashed line. So the difference here is also on the order of 20 kilometers, where the receiver functions indicate a MOHO pick at about 40 kilometers depth, and the deepest part of the virtual deep seismic sounding is more at 60 kilometers. And so these authors attribute this discrepancy also to the presence of a high velocity lower crustal layer. So this is a study from Shin et al. Published earlier this year that is a joint inversion of surface waves from ambient noise and also receiver functions. So being a joint inversion of multiple techniques, perhaps it's a little bit more robust than one technique alone. These profiles where they both encounter the Wyoming Craton are shown on the right, where you can see the high velocity layer in purple, and these crustal thicknesses are more on the order of 50 kilometers. So despite the high temperature geochronology and mineralogy that suggests that the history of the deep crust in central Montana is fairly dynamic, the overall thermal history is actually one of essentially monotonic cooling for the last 1.5 billion years. So Terry Blackburn has been doing quite a bit of high precision thermochronology with different accessory minerals, titanite, rutile, apatite. This is rutile data. And modeling that data suggests essentially that the temperature near the base of the crust in this area has been at or below about 500 degrees for the last, or since the Mesoproterozoic. So that's one way to think of, or another way rather, to think of the age of the high velocity structure or deep structure in this region, but that doesn't necessarily mean that lower temperature modifications to the crust haven't occurred during subsequent events, and so that's where I want to get next. So this is the Shin et al. Joint inversions again, and I'm just showing it again to illustrate that generally as you go from north to south from the Montana and Wyoming region into the Colorado Plateau, these are shear wave velocities in the lowermost 4 kilometers, I think, just above the MOHO. But the shear wave velocities or the seismic velocities gradually decrease as you get into the Colorado Plateau. And also this generally corresponds to a rise in elevation in the Southern Rockies too. And how and when we got elevation gain in the Southern Rockies has been a topic that has been debated for a long, long time. And there are a number of different mechanisms that have been put forth. Is it crustal thickening that is laramide in age? Is it Rio Grande Rift related? Is it mantle flow dynamics? Is it widespread hydration of the mantle? And the latter has been documented in a number of xenolith localities throughout the Rocky Mountain region, anywhere from central Montana to southern Wyoming to the Colorado Plateau. But dating this metasomatic effect, the hydration, has been notoriously difficult. A number of studies from a number of different localities suggest that some of this metasomatism is as old as Proterozoic. Others suggest that it may be as young as Cenozoic. And probably some of the most convincing arguments for a Cenozoic age for that mantle hydration comes from the Colorado Plateau, from mantle peridiotites and eclogite xenoliths that have been studied there. But the concept of crustal hydration has received a lot less attention, probably in general because there's much less documentation of it. But certainly one of the areas that these effects have been documented by multiple studies has been in the Colorado Plateau from the Navajo volcanic field. So Silverstone et al. Argues that that hydration is probably Proterozoic, but there are no direct age constraints on that hydration. So that's what this sample is. This is one of Silverstone's samples that a master's student at CU is working on that displays extensive hydration. This is a potassium X-ray map on the left and a calcium X-ray map on the right that illustrates probably the most prominent textural manifestation of this hydration, where high temperature feldspars are being altered to a low temperature but still high pressure assemblage of albite and high silica phengitic muscovite. So you can see the relic core in this calcium map of plagioclase that's been eaten away along the margins. The potassium map shows phengitic muscovite that is growing along these altered margins. And the other thing that is that I'm illustrating here with these blue dots are secondary monazite that is associated with this alteration assemblage. So we've been dating the monazite by thorium lead at UCLA with the ion probe. And the overall results are shown on the left, the upper left here. So we see evidence for monazite growth during multiple periods dating back to the Mesoproterozoic, but the bulk of the data is late Cretaceous. And so the dates during the late Cretaceous time are shown on the right, and we see evidence generally for progressive or continuous, more or less continuous growth of monazite, and by extension, I think I would argue that the hydration effect occurred over about a 30 million year period between about 90 million years and just under 60 million years ago. So this is the time of the laramide orogeny. This is the time that shallow subduction of the Farallon slab has been proposed, that hydration of the upper mantle has been proposed. So I think I'd argue that not only did those fluids get into the upper mantle, but they also penetrated into the lower crust and even the middle crust. This xenolith is actually more of a mid-crustal xenolith. So it's very hard to say what the spatial extent of this hydration effect was or is in the crust. But certainly if it's extensive enough, then the de-densification effect, especially in more garnet-rich lithologies where garnet would be consumed during that hydration, could be enough to have driven some of the elevation gain that we need to get to the elevations of the Rockies today. So I've shown some quick results of a variety of different techniques that we've used to look at xenoliths, and I think we've learned a lot. There's obviously a lot more that could be learned, I think. I like to emphasize the heterogeneity in the deeper xenoliths from Montana to point out the composite origin for the high velocity layer. Potential intra-layer velocity steps may be complicating the crust mantle, the seismic definition of the crust mantle boundary. And preliminary geochronology from these Colorado Plateau xenoliths suggests that the hydration in those xenoliths is laramide in age. And I hope that that's one area where seismology and additional geophysical data may be able to help us evaluate just what the spatial extent of those types of effects are. Thank you.